The goal of this video is to bring together two strands of what we've learnt in the course so far. The two strands are frequentist inference and empirical distributions. Let's remind ourselves what they're about. Frequentist inference says that the data we happen to see in our reality can be misleading because of noise. And what we should do is look across the whole multiverse and think of all the parallel universes and all the data sets in those universes and think about what estimates the parallel universe data scientists made. To do this, we need to somehow simulate the multiverse. In other words, we need to be able to generate synthetic data sets that reflect what might have happened but didn't. In the last two videos, the simulation strategy we used was simple. We propose a probability model, we fit its parameters, and then we just generate a dataset by sampling values from the fitted probability model. But there's a viewpoint that says it's daft to fit probability models. When we looked at empirical distributions, we came to the conclusion that there's no need to do any work at all to fit a distribution. We can get a perfect fit just by using the empirical distribution. The slogan is, a dataset is a distribution. If we want to generate new values from the distribution behind the data, we should just pick values at random from the dataset itself. Let's see what happens when we bring these two ideas together. Let's start with a simple confidence interval. This question presents us with a dataset consisting of readings from two groups and asks us to find a confidence interval for the difference between the means from the two groups. Here's the code. This is just the usual three-step procedure for finding a confidence interval. Steps 1 and 3 are exactly the same as before. What's different here is step 2, generating a synthetic dataset. What this code does to create a synthetic copy of the X dataset is just sampling from the empirical distribution of X. This is the best possible fitted distribution for X, and likewise for Y. This approach is called non-parametric resampling for the obvious reason that it doesn't need any parameters to be estimated. I love this sort of code. It's just a handful of lines, but to understand the thinking behind it, we need so much work, so much careful thought about what exactly we're trying to answer. Okay, so that's non-parametric confidence intervals. Next, let's look at non-parametric resampling for hypothesis tests. Same dataset, but now we're asked to test whether the two groups have the same distribution. Here's the code. Again, steps 1 and 3 are exactly what we did before in the last video, Fisher's procedure for hypothesis testing. The only difference is step 2. For step 2, we have to generate a synthetic dataset under the assumption that H0 is true. So let's think, first of all, what is H0 for this question? The question tells us, test whether the two groups have the same distribution. In other words, it's asking us to test the null hypothesis that there's a common distribution from which X and Y are both sampled. And what's the empirical way to get a perfect fit for that common distribution? Simple. If all the values, all the X and all the Y, come from a common distribution, then the best possible fit is the empirical distribution of all of those values. So now it's easy to see how to generate a synthetic dataset under the assumption that H0 is true. If H0 is true, then both X and Y are drawn from that common distribution. And that's exactly what we did. All of this probably looks too good to be true. I warned you earlier about parametric resampling, and the same warning applies to non-parametric sampling. Any method for simulating the multiverse is a leap of faith. It has to be. How could we possibly deduce what might have happened when all we know is what did actually happen? There aren't any mathematical guarantees about the validity of these procedures. The only way to give a guarantee would be if we knew the correct model for what's actually going on in the multiverse. Mathematicians are welcome to assume that if they want, but data scientists should know better. They know that every model is wrong. So in practice, you think about the problem you're trying to solve and you ask yourself if your resampling strategy is reasonable. Or you give up and you convert to Bayesianism. But then you also have a problem which is just as intractable of where on earth your prior beliefs are meant to come from. The deep answer is that we need to think again about the problem we're trying to solve. In later videos, we'll talk about validation and why it supersedes both the Bayesian and the frequentist approaches.